Hello, welcome back. Once again, we're back to some chemistry. We've got Big Idea 2, Part 2. This one I'm going to be talking about covalent bonding, how that works into polarity. So we talked about covalent bonding as essentially a part of electrostatic attraction. So at some point or another, you have to have positively charged things and negatively charged things coming together. So covalent bonding, it's a little bit more how should we say, a little bit more disguised because there's this sharing thing. So covalent bonding, the whole idea in covalent bonding is that there's this constant sharing of electrons, right? And so when you're sharing electrons, each atom, and what's separate about this is that each atom, let's say we have water, so water, each hydrogen has one electron, and oxygen has 6 electrons, naturally. Now, of course, oxygen wants 8, and hydrogen only needs 2 to complete its outer shell. So they will share these electrons between them. So oxygen actually counts these shared electrons here as its own, right? And then hydrogen counts these electrons as its own, as well as the oxygen will count all of these electrons as its own. So the shared electrons, each atom acts as if they're its own electrons, and so then that causes it to be this group right here. So within the sharing, everything is stuck together. So this is a covalent bond. All right. Ooh, looks like a nice bunny rabbit, doesn't it? There's eyes, whiskers. Hi, kids. So anyways, so this is bonding in the covalent style with sharing like that. So let's look at a couple of examples here, and will be pretty quick. So if you have 2 hydrogen sharing, here they go, like they only need to have 2 electrons, so they're sharing these 2 right here. There you see the bond between the 2 of them right there. And here fluorine, similar kind of thing, 2 fluorine atoms each need 1 electron to complete 8, and so they get together, and these 2 are shared in between the 2. All right. Now some covalent bonds, such as carbon dioxide, there's multiple sharing of electrons. So carbon has these 4 blue electrons here, and then the oxygen each brings, carbons are these orange ones. These blue ones actually belong to the oxygen molecules. Now you'll notice that carbon shares every single one of its electrons, and in it, of course, takes 2 electrons from each oxygen. So there's a total here of 8 sharing electrons between these. So this is what we would call double bonds. So these double bonds right here are going to bring the proximity of these actually really close together, because that's really strong, whereas this single bond right here is not necessarily going to bring these 2 that close together. So the more bonds they have, the closer together. And you see here with this carbon atom in the middle, it actually has 4 different places where it's bonding. And so carbon often shares every single one of its electrons with everything around it, which is why it's used to create biological life. All right, so let's look at these bonds real quick. When you're talking about just a bond, a single bond in between 2 atoms, what ends up happening is this sharing occurs centered in between the 2 nucleuses, and we call that a sigma bond. So if we had 2 sigma bonds that were both s orbital bonds, they would look kind of like this. It's 2 round balls. The bond axis would be straight through the middle, and the nucleuses are right in the center, and so this bond is totally centered. So here would be a sigma bond between 2 p orbitals, right? So here's the 2 p orbitals right here, bond axis right through the middle. Here's the nucleuses of each of the atoms, and here's the bond right here, perfectly centered in between those 2 nuclei. So that's a very strong bond. Now when you get to a pi bond, here's what's going to happen. If you have a double bond like we see here, so see between each one of these carbons and oxygens, we have 2 bonds. Well, a sigma bond, we said, was centered perfectly. And actually, they show these each off center, but what's actually going to happen is one of these bonds will be centered, making the second bond off-center from the two nuclei. And so here's kind of what it's going to look like. So if here's the two nuclei right here, that bond is going to be off-center up here on top of that, you see. And so here's kind of the bond axis between the two. And so this off-center bond is going to hold it together, but you see here's where the actual center of the nucleus is. And so it's going to hold it not quite as strongly as the sigma bonds. But as soon as you get more than one bond, you can't have everything centered. So there's always only one sigma bond, and if we have a single bond, it's always a sigma bond. If we have a pi bond, it's because we have a double bond now, so we have one sigma and one pi. So all double bonds have one sigma and one pi. And so if we talk about strength of the bonds, a sigma bond is the strongest of all the bonds. But if you have a double bond, it's going to be stronger than a single sigma, but it won't be twice as strong because we talked about how these off-centered pi bonds are not quite as strong as a sigma bond. So it will be stronger, but it won't be twice as strong. But if you had an atom with double bonds, it'd be closer together than an atom with single bonds, because we've got double the pull on each one of these and double the sharing going on. Well, actually, like I said earlier, not quite double. And the same would be true if we had a triple. So that would be an even closer bond. This would be an even stronger bond, but it wouldn't be triple the strength of a sigma because each pi bond is weaker than a sigma bond because it's off-center. But this would still be stronger than this, and this stronger than this. As far as bond length goes, as you can see from my very nice drawing, this is going to be the longest. So a sigma bond is going to be the longest just because it simply only has one. A double bond is going to be intermediate, and then this one is going to be the shortest because it has triple holding it together. All right, so let's look lastly at polarity. So whenever we're sharing electrons, if you look here, oftentimes what happens is that one of your atoms, in this case nitrogen, so if we look at nitrogen, one of your atoms is going to have a stronger electronegativity. And if you remember, electronegativity is how hard it pulls electrons to itself. So this nitrogen right here, having a very strong electronegativity, is going to pull all the negative electrons really closer to itself. And if it does that, if the electrons actually tend to be around the nitrogen more, well, that's going to create kind of a positive end over here. And that's what polarity is, where you can find one end of the molecule is positive and the other end of the molecule is negative. Now, what's going to happen in that case, if you have this molecule which kind of has this positive negative end, well, they can then match up to any other positive negative molecule. So polar substances will stick together, they'll dissolve in each other, whereas nonpolar won't. So let's look right here. So this one is also polar because what's happening here is the electrons are all going to be sucked closer to this chlorine, very highly electronegative, and then hydrogen is not very electronegative. So oftentimes hydrogen makes polarity when it's combined with other elements, and so we actually call that a hydrogen bond because hydrogen bonds, well, if I was to stick two of these together like this, it would be a hydrogen bond. And here's what would happen. This positive end from the next molecule would stick right here, right? Because that's the negative end of this. Now, if we look at this, why is this one non-polar? Well, if you look here, it's got chlorine on all ends. And chlorine isn't going to be able to pull harder than chlorine. And so this particular element is going to have an equal pull of electrons all the way around. So you're not going to find one end of it positive and one end of it negative. It's all going to be the same. And so that's what we get with nonpolar. So nonpolar things, because they don't have this positive negative, and they tend not to stick to each other. They tend to be gases, more or less. So this is carbon tetrachloride right here. They also, if you have something that's nonpolar, it will exist with nonpolar, dissolve in nonpolar, but it will totally be repelled by this and not be able to be dissolved by this. So nonpolar dissolves nonpolar, and polar dissolves polar. There's going to be a whole lot more about polarity as we go on, but essentially those are the two things that you need to know: is that polar polar molecule is created by an unequal pull, and a nonpolar is created by an equal pull all the way around. So hopefully this was enlightening and helped you out a lot.